The 80% rule was a convenience, not based on foundational principles, and was inconsistent. Its primary application was branch circuits. It was not applied to feeders, which would have been reasonable. The National Electrical Code is very clear about sizing conductors. Firstly, calculate the load. Secondly, pick the appropriate ampacity. Thirdly, apply all correction factors. The capacity of the circuit is determined this way, not by an arbitrary rule of thumb. This is still the case, and the number of wires undersized because of this rule is probably greater than the number undersized without it. The 80% rule is harmful. It is beneficial to see it removed. An extension to panels based upon their total connected load is not necessary. Considering the rule on existing installations, especially after additions or modifications, has value. However, it is not practical, and too many inspectors will not enforce it. Branch circuit derriting for a long run is another myth that should be buried. Electricians will use this to get around a permit, or not charging for unnecessary work. Calculating the load involves determining the total current that the circuit is expected to carry. This includes both continuous and non-continuous loads. Continuous loads are those that are expected to operate for 3 hours or more at a time. The National Electrical Code requires that continuous loads be limited to 80% of the branch circuit rating. Non-continuous loads are those that are not expected to operate for 3 hours or more at a time. The ampacity of a conductor is the maximum current that it can carry continuously without exceeding its temperature rating. The National Electrical Code provides tables that list the ampacities of different types of conductors based on their size and insulation type. Correction factors are used to adjust the ampacity of a conductor for various factors, such as ambient temperature, the number of conductors in a raceway, and the type of insulation. The National Electrical Code provides tables that list correction factors for different conditions. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overheating and causing a fire. The National Electrical Code requires that overcurrent protection devices be sized to protect the conductors that they are connected to. The 80% rule prior to its removal stated that the continuous load on a circuit breaker should not exceed 80% of the breaker's rating. For example, a 20 amp breaker should not have a continuous load of more than 16 amps. The rationale behind this rule was to prevent the breaker from overheating and tripping unnecessarily. It was believed that if a breaker was loaded to more than 80% of its capacity, it would be more likely to trip due to the heat generated by the current flow. The National Electrical Code determined that the calculations used to size conductors and overcurrent protection devices already account for the potential for overheating. These calculations take into account factors such as the ambient temperature, the number of conductors in a raceway, and the type of insulation used. Therefore, the 80% rule was deemed to be unnecessary and was removed. In older electrical installations, the conductors and overcurrent protection devices may not have been sized using the same rigorous calculations that are used today. It is possible that these installations may be more susceptible to overheating if they are loaded to their full capacity. Therefore, it may be prudent to apply the 80% rule to these installations as a safety precaution. When adding new loads to an existing electrical installation, it is important to carefully consider the capacity of the existing circuits. If the existing circuits are already loaded to near their full capacity, it may be necessary to install new circuits to accommodate the new loads. It is also important to ensure that the conductors and overcurrent protection devices are properly sized for the new loads. Understanding conductor sizing involves several steps and considerations outlined in the National Electrical Code. Firstly, determine the application. This involves identifying whether the conductor is for general use, a motor circuit, or other specific applications, as each may have different requirements. Secondly, calculate the load current. Calculate the continuous and non-continuous loads that the conductor will carry. Continuous loads are those that operate for 3 hours or more. The National Electrical Code requires continuous loads to be limited to 80% of the overcurrent protection device rating unless the assembly is listed for operation at 100% of its rating. Thirdly, apply derriting factors. Adjust the conductor's ampacity for ambient temperature, the number of conductors in a raceway, and other conditions as specified in the National Electrical Code tables. Fourthly, select the conductor size. Choose a conductor with an ampacity after directing that is sufficient for the calculated load current. Fifthly, consider voltage drop. Check the voltage drop to ensure it's within acceptable limits, especially for long runs. The National Electrical Code recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. Sixthly, select the overcurrent protection. Choose a circuit breaker or fuse with a rating that protects the conductor while allowing for motor starting currents or other temporary overloads. The overcurrent protection device should not exceed the conductor's ampacity. It's also important to note that some equipment, such as air conditioning units or machinery, may have specific conductor sizing requirements listed on their nameplates. Always refer to the equipment's documentation and the National Electrical Code for accurate and safe conductor sizing. The National Electrical Code Article 310 covers conductors for general wiring. This article provides tables and guidelines for determining the allowable ampacities of conductors based on their insulation type, size, and installation conditions. It also covers topics such as conductor identification, minimum sizes, and ampacity correction factors. The National Electrical Code Article 430 covers motors, motor circuits, and controllers. This article provides specific requirements for sizing conductors and overcurrent protection devices for motor circuits, taking into account the motor's starting current, running current, and duty cycle. The National Electrical Code Chapter 9 contains tables and examples that are used throughout the code for various calculations and applications. These tables provide information such as conductor properties, conduit dimensions, and box fill calculations. Ambient temperature affects the ampacity of conductors. Higher ambient temperatures reduce the ability of a conductor to dissipate heat, which lowers its ampacity. The National Electrical Code provides correction factors to adjust the ampacity of conductors based on the ambient temperature. The number of conductors in a raceway affects the ampacity of each conductor. When multiple current-carrying conductors are installed in a raceway, the heat generated by each conductor can increase the overall temperature within the raceway, reducing the ampacity of each conductor. The National Electrical Code provides adjustment factors to reduce the ampacity of conductors based on the number of conductors in a raceway. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to operate inefficiently or not at all. The National Electrical Code recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Overcurrent protection devices such as circuit breakers and fuses are designed to protect conductors from overheating and causing a fire. These devices interrupt the flow of current when it exceeds a predetermined level. The National Electrical Code requires that overcurrent protection devices be sized to protect the conductors that they are connected to. Short circuits occur when there is a low resistance path between two conductors, causing a large amount of current to flow. This can quickly overheat conductors and cause a fire. Overcurrent protection devices are designed to quickly interrupt the flow of current during a short circuit to prevent damage. Ground faults occur when there is an unintentional connection between a conductor and ground. This can create a shock hazard and can also cause a fire. Ground fault circuit interrupters are designed to detect ground faults and quickly interrupt the flow of current to prevent injury or damage. Arc faults occur when there is an unintentional arc of electricity between two conductors. This can create a fire hazard as the arc can ignite nearby materials. Arc fault circuit interrupters are designed to detect arc faults and quickly interrupt the flow of current to prevent a fire. Electrical panels are enclosures that contain circuit breakers or fuses that protect the various circuits in a building. Electrical panels should be properly sized to accommodate the expected load. The electrical panels should be installed in a readily accessible location. The electrical panels should be properly labeled to identify the circuits that they protect. Grounding is the process of connecting electrical equipment to the earth. This helps to protect people from electric shock and can also help to prevent fires. All electrical equipment should be properly grounded in accordance with the National Electrical Code. Bonding is the process of connecting different metal parts of an electrical system together. This helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electric shock. All metal parts of an electrical system should be properly bonded in accordance with the National Electrical Code. Electrical safety is of paramount importance. Firstly, always turn off the power before working on any electrical equipment. Secondly, use properly insulated tools and equipment. Thirdly, never work in wet conditions. Fourthly, be aware of your surroundings. Fifthly, if you are not comfortable working on electrical equipment, hire a qualified electrician. Electrical permits are required for many types of electrical work. This is to ensure that the work is done safely and in accordance with the National Electrical Code. Contact your local building department to determine whether a permit is required for your project. Electrical inspections are conducted by qualified inspectors to ensure that electrical work is done safely and in accordance with the National Electrical Code. If you are having electrical work done, be sure to schedule an inspection. The National Electrical Code is a set of standards for the safe installation of electrical wiring and equipment. The National Electrical Code is updated every 3 years. The National Electrical Code is adopted by most states and local jurisdictions in the United States. The National Electrical Code is a valuable resource for anyone who works with electricity. The National Electrical Code covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and bonding. It is essential to consult the latest edition of the National Electrical Code for the most up-to-date information.